So good day everyone. For today we're going to answer three physics problems that we got in the University Physics with Modern Physics book, Volume 1, 14th edition. So for today we're going to talk about problems under Chapter 17, Temperature and Heat. So let's get started. So for our first problem, which is about thermal expansion, a copper cylinder is initially at 20 degrees Celsius. At what temperature will its volume be 0.150% larger than it is at 20 degrees Celsius? So we're going to look for the temperature in this problem. So increase in volume due to the change in temperature is simply given by this equation, delta V equals V sub 0 beta delta T, where V sub 0 is the initial volume, beta is coefficient of volume expansion given that volume increases by 0.115%, while delta T is increase in temperature. After copper cylinder undergoes volume expansion, new volume becomes V is equal to V sub 0 plus 0.15 over 100 V sub 0. So we're going to get an answer of 1.0015 V sub 0. So the next step is we're going to look for the increase in volume. So our earlier equation, which is delta V, which is equal to V minus V sub 0, it will yield to delta V over V sub 0, which is equal to 0.0015. So after that, we're going to rearrange the equation. Delta V equal to V sub 0 beta delta T for delta T. So we need to look for delta T. We're going to rearrange it with respect to delta T. So we're going to have an equation of delta T equal to delta V over V sub 0 times beta. And then we're going to substitute this one for V sub 0. So it will be 0.0015 over beta. And then after that, we're going to substitute the coefficient of volume expansion of copper, which is 5.1 times 10 raised to negative 5 degrees Celsius. So we're going to plug it in our equation. So delta T is equal to 0.0015 over the coefficient of volume expansion of copper, and we're going to get an answer of 29.4 times degrees Celsius. So we're just going to check if it's correct. Okay, correct. And then therefore, expression for the required temperature is T is equal to T sub 0 plus delta T, and delta T is what we have computed here. So we have an T sub 0, which is this one, the initial temperature. So the initial temperature plus the change in temperature that we have computed, we're going to have an answer of 49.4 degrees Celsius. For our next problem, a surveyor's 31.0 meters steel tape is correct at 20 degrees Celsius. The distance between points as measured by this tape on a day when its temperature is 5 degrees Celsius is 25.970 meters. So what is the true distance between the points? So for this one, the expression for a linear expansion of an object is simply delta L over L equal to alpha delta T, wherein delta T is the change in temperature, alpha is the coefficient of linear expansion, while L is the length of object. So for the next one, change in length of the steel tape, we have delta L, which is equal to L sub 1 minus L sub 2, wherein L sub 1 is the measured length of the tape, while L sub 2 is the actual length of the tape. So the next one is change in temperature of the steel tape, wherein delta T is equal to T sub 1 minus T sub 2, wherein T sub 1 is the temperature at distance measured, while T sub 2 is the temperature, which steel tape is a steel tape. And then after that, since we have all the equations that we need, we're going to substitute the value of delta L and delta T in the equation. So we're going to have L sub 1 minus L sub 2 over L sub 2 equal to alpha change in temperature. So after that, we're going to substitute the given values that we have. So L sub 1, which is the measured length of the tape. So actually, in this problem, we're going to look for the actual length of the steel tape, the true distance of the steel tape. So and then we have the temperature at distance measured, which is 20 degrees Celsius, and we're going to convert it into Kelvin. So 20 degrees plus 273 is equal to 293 Kelvin. Well, for T sub 2, the temperature at which steel tape is a steel tape, we have 5 degrees Celsius converted into Kelvin plus 273. We're going to have an answer of 278 Kelvin. And then for the coefficient of linear expansion of a steel tape, I guess, the steel tape, we have 12 times 10 raised to negative 6. So after that, we're just going to plug all the values that we have, and then we're going to get an answer of 25.965 meters. So for problem number 3, our last problem, which is all about mechanisms of heat transfer. Our problem is a spherical pot contains 0.75 liters of hot coffee, essentially water, at an initial temperature of 95 degrees Celsius. The pot has an emissivity of 0.6 and the surroundings are at 20 degrees Celsius. So calculate the coffee's rate of heat loss by radiation. So in this problem, radiation is mentioned. So radiation is a mode of heat transfer where the heat transfer takes place by electromagnetic radiation, and every surface of the body emits some forms of radiation in form of electromagnetic radiation. So in this problem, the first thing that we need to do is to convert the value of the volume from liters to cubic meters. So we have a value of 0.75 liters as mentioned earlier, multiplied it to 10 raised to negative 3 meters cubic meters. So we're going to have an answer of 75 times 10 raised to negative 5 cubic meters. So since the volume of sphere is given, V is equal to 4/3 pi r cubed, wherein r is the radius of the pot, we need to rewrite the equation in terms of r. So since we need to look for r, we're going to rewrite the equation. So basically, when we isolate this one will be transferred to the this one will going to be divided by 4/3 pi both sides, and then we'll cancel here, so r cube will be left. And then since we need only the value of r, we're going to get the cube root of the equation. So we have an equation of r is equal to cube root of v times 3 over 4 pi. So substitute the value of v that we have converted earlier. So we're going to have an answer of 0.05683 meters. And then we are given the value of the surface area of the pot, wherein it is A is equal to 4/3 pi, A is equal to 4 pi r squared. So substitute the value of r in the surface area equation that we have computed earlier, which is 0.0563. So substitute, and then we're going to have an answer of 0.03983 meters squared. So in calculating the heat loss, we need to use the Stefan-Boltzmann equation. So I'm going to use this one. H is equal to A E this times T initial raised to 4 minus T, T initial minus T S raised to 4. So A is the surface area of the pot, E is the emissivity of the pot, which is given earlier, while this one is the Stefan Boltzmann constant, and this one is T sub I is the temperature of the pot, and T sub S is the temperature of the surroundings. So before anything else, we need to convert the temperature and the surrounding temperature. Since both of them are in degrees Celsius, we need to convert it into Kelvin. We should always remember that we need to convert the temperature if it's in degrees Celsius, we need to convert it into Kelvin. So here we converted, so we have an answer of 368 and 293. So after that, we're going to substitute the given values to the Stefan Boltzmann equation. So this one is the area that we have calculated earlier. This is the emissivity, which is given in the problem, and this one is the constant, Stefan Boltzmann constant, and this one is the temperature of the pot and the temperature of the surroundings. So all in all, when we multiply them, we're going to get an answer of 14.864 joules per second. So the heat loss is 15. That's all. Thank you.